Hello, this is the second and last video of our Solarcv project Unit 1, and we will study the evaluation of potential generation. In following units, we will study the main characteristic of our solar thermal power plant, for example the HTF system, the solar field or pumps. However, first we must convince other people to invest some money in our project. For example, we must carry out a solar study to convince these people, for example a bank. Previously, to understand these concepts, we must overview previous terms that we studied in last unit. Irradiance means the amount of energy, of power, which is received by a given area, and its units are watts per meter square. And if we translate this concept for a given period, we are going to have irradiation. Irradiation means the amount of energy received for a given period of time for a definite area, and its units are kilowatt-hour per meter square and per year. In the same way, we are going to have the different kind of irradiation. Direct irradiation is the irradiation power that reaches a certain area without having undergone any change in its direction. Direct normal irradiation, DNI, is the direct irradiation measured on a surface perpendicular to the direction in which the sun rays are received, and we are going to measure this DNI with a perihelimeter. On the other hand, we have diffuse irradiation. We are going to lose a part of the irradiation due to the dust particles, mountains, oceans. On the other hand, we have reflected irradiation, and this is the type of radiation which is reflected due to the Earth's surface, and it depends of the reflection coefficient. For example, if we have a surface with 100% of reflection coefficient, all the incident energy is going to be reflected. Global irradiation is the total irradiance or the global irradiance, and is made up from direct, diffuse, and reflected irradiation. And now in this unit we are going to discover a new concept, and this is corrected DNI. We have that a surface has a normal vector, and we are going to have another vector due to our solar ray. If the vector of our solar ray and the normal vector of our surface are the same, the incidence angle would be 0, and the cosine of 0 is 1. So the DNI and the corrected DNI would be the same. However, if the incidence angle is not 0, the cosine of an angle which is not 0 wouldn't be 1. So we are going to have some losses, and this is going to affect the performance angle. Now, to carry out our solar study, we must collect data from public databases. We have that the first step to carry out the solar study is to obtain data from public databases. And some public databases are free, or others we must pay because they have been developed by other companies. The time between measurement and measurement is very important because it determines the accuracy of the system, which can be daily, hourly, or monthly. It's pretty obvious that if we have from measurement and measurement that the period between each measurement is 1 hour, is going to be more accuracy than if one measurement and another measurement there is a period of a month, for example. And it's recommendable that this data have indicated the clockwise angle, azimuth angle, and incidence angle, because as we saw in the previous unit, to elaborate the tracking system we must define are very important, the clockwise angle and the incidence angle. The most important public database is satellite, which can be found in internet. As we saw at the beginning in this unit, the operator or the engineers are not going to invest no money, but this money is going to be invested by a bank. So we must convince these people, this bank. So we must elaborate a very useful solar study. To elaborate this are very useful on-site data. This on-site data, aside from the radiation data obtained from the databases, an exhaustive study of the solar study is required. For example, hourly direction, speed and frequency wind measurements, temperature hourly measurements, hourly humidity measurements, and rainfall. But it's very useful to take into account that it's not very important rainfall, but the most important is the number of hours with diffuse radiation without direct radiation, because when we elaborate the irradiation for a given period and for a given area, we are gonna do the weighted mean instead of arithmetic mean. In following picture, we will see why. And the number of hours with variable cloudiness, because in general we are not going to consider days with a great percentage of the day with cloudiness. Now here we can see a weather station, and the main instruments are a vane, which determines the wind direction, the anemometer, which determines the speed, the wind speed, the pyranometer, which determines the global irradiation, although many weather stations have a perihelimeter, which determines the direct irradiation, and a thermohygrometer, which determines the temperature and humidity. Now we must define a very important concept, and this is solar year type. Solar year type is the weighted mean of the radiation that is received in each period of 10 minutes throughout the year. This is a weighted mean instead of arithmetic mean because, for example, if we have some data, for example 20 data, and their mean and its mean is 20, and another amount of data, for example 30 data, and its mean is 25, they are not going to support the same, the amount of 20 and the amount of 30. But we must do the product between 20 by its mean and 30 by its mean divided by the total number of elements. So the solar year type is the product of the number of minutes belonging to this total of 10 minutes which has irradiation. And now we can elaborate three tables. The first table it reflects the average calculated over 15 years. The table 2, it reflects the data obtained from on-site data. And the table 3, it reflects the average between table 1 and table 2. And now we can elaborate two plots. In the first plot, we are able to see the irradiance, that is watts per meter square, per hour and per month. So really we are going to see the irradiation. And the second plot, with a scale from 0 is the minimum to 10 is the maximum, the global irradiance and the direct normal irradiation, DNI. And here we can see that we have time meteorological year, which is the weighted mean, and mean, which is the arithmetic mean. However, we must define some concepts that we must not take into account in a solar study because there are some defects. Although we have some irradiation data, this is just a general idea because it's mandatory to compare the annual irradiation data and irradiation every 10 minutes. It's pretty obvious that irradiation every 10 minutes are going to be more accuracy. Choose a quality database, as we saw that the main parameters which determine the quality of a database is data surface. The smaller surface is going to be the more accurate the study, and data time, the smaller time between each data is going to be the more accurate the study. A solar thermal power plant is expected to be working at least 30 years, so it doesn't matter if more time is spent than it was expected at the beginning. we must compare wind data and radiation data and delete the days which don't let operate the plant. That is, if we have a day which has a lot of hours with cloudiness, we're not going to consider for our purposes, because this day won't support the enough energy to let operate the plant. And it's necessary to study the variable cloudiness, as we saw, because to estimate the production generated on, for example, X operative days, because in general a day of variable cloudiness can be considered as a totally cloudy day. So this day is not going to be considered inside of X operative days. Another important concept in our solar thermal power plant is efficiency, because we are going to have some irradiation in our mirror, and the optical performance is going to determine how much of this energy is going to be reflected into the absorber tube. The thermal performance, which is the amount of thermal energy which would be able to operate, and previously we are going to have an incidence angle, because as we saw, if this incidence angle is not zero, that is, if the normal vector of the mirror and the vector which belongs to our solar ray don't match, the cosine of a number which is not zero wouldn't be 1, we are going to have a performance of our turbine. Finally, we are going to have a generator performance, which is going to be finally the electrical energy delivered to the network. For example, in this case, we are able to see the efficiency for a module, although this concept we will see widely in the Unit 3 solar field. For example, here we are able to see a data sheet, and the most important parameters are these: performance specification, absorber area, really is the catchment area in a solar mirror. Zero loss efficiency is pretty obvious, and this is the maximum efficiency if the normal vector of our mirror match with the vector of our solar ray. And the different heat loss coefficient, we are going to have a first order and a second order. Another important concept is production estimation. We can estimate our production estimation of the solar thermal power plant with public database, instruments data, and the incidence angle. Although nowadays it's very important to take into account that it's available some software. We can acquire some software from other company. Although we can develop this company, we can develop our own software, or even we can acquire free online software but contrast it. In this case, one of the best software has been developed by company NREL, belonging to United States government, and its name is SUN. SUN is the acronym of Solar Advisor Model, and it can be downloaded in this page. And if we define some concepts, for example, the solar thermal power plant features and the solar year type data, we are going to obtain the electrical energy theoretically obtainable, the plant rated power, solar field size, features of installed components, and meteorological features. Here we can see a picture of the program. Now we must define the power rating in a solar thermal power plant. First, we must understand what is power rating. Power rating of equipment is defined as the highest power input allowed to flow through particular equipment. In this case, the power rating of the solar thermal power plant will be the maximum power produced under nominal conditions. In a solar thermal power plant, this power rating will be limited by three main factors. This is the optimum power and technical economical point of view, that is the overall performance, really, the maximum possible capital, how much money we have, and the power rating legal limit. For example, in Spain, the maximum power for a solar thermal power plant is 49.9 megawatts. So if we have enough money, we are going to limit this power for our plant. However, we must consider another important concept, and this is the difference between energy and power. Electrical energy is the form of energy that results from the existence of potential difference between 2 points, and it's going to allow establishing an electrical current between both points, and it's measured in joules, although for our purpose it's going to be measured in watts-hour. And we have, on the other hand, electrical power. Electrical power is the amount of energy per unit of time. Really, we must think that energy is the amount of power for a given period. So this is going to be measured in watts, which is joules per second. To understand easily this concept, we are going to study an example which is very useful to understand this. With this easy example, we are able to understand this concept. We have that the plant has produced 1000 watts from 1 p.m. to 2 p.m., 500 watts from 2 p.m. to 3 p.m., 0 watts from 3 p.m. to 4 p.m., and 1500 watts from 4 p.m. to 5 p.m. But if the plant always is working, why from 3 p.m. to 4 p.m. the plant has not produced nothing? We must understand this. We have our solar array here, and this solar array is going to be reflected in these mirrors, and is going to hit the HTF. The HTF enters here and is heated along this observer tube. The HTF is going to have an energy, and this energy is going to heat the water in liquid state to steam state, and this steam state water is going to move the high pressure turbine and low pressure turbine, and this turbine is going to do a exercise work in the generator, and the generator is going to give the network the electrical energy required. However, if this HTF hasn't got the enough energy to heat the water from liquid states to steam state, or even to superheat this liquid, the plant is not going to be able to produce nothing. So really, we are going to have always irradiation, but if this irradiation is not higher of a required limit, for example, I don't know, 400 watts, if the irradiation here is not higher than this limit, we are going to consider zero irradiation from 3 p.m. to 4 p.m. for this period. So we must understand now the difference between energy and power. Power is the instantaneous energy. So we are receiving energy from the space for a second, for example. However, energy is the sum of the power for a given period. For example, we are receiving here, we have an irradiation of 400 watts per meter square. If we have a solar field of 5 meters squared, the power will be 2000 watts. Okay? However, this irradiation is for a given period, for example, 1 hour. So we can define that this energy would be 2000 watts per hour. And this isn't a power, this is an energy. For example, in this case, we have 1000 watts from 1 p.m. to 2 p.m. So we are going to have 1000 multiplied by 1 hour plus 500 multiplied by 1 hour plus 0, because this irradiation is not higher than the required limit. So 0 multiplied by 1 hour plus 1500 watts multiplied by 1 hour. And the total amount is 3000 watts per hour. Although you can imagine that this energy has been obtained in 4 hours, and that's true because this is from 1 p.m. to 5 p.m. Really, this term has units like watts per hour. This is the same that if we have these terms, or if the plant had produced 3,000 watts in just 1 hour, or for example 750 watts in 4 hours. So really the energy is the power for a given period. For example, in this picture we are able to see the expected power of a 50 megawatts thermal power plant with thermal storage, for example in Andalusia, Spain. Here is the mean power, megawatts, and this is the legend. These are the hours, and these are the months. And we can see that the main power, the highest power, is produced from 8 p.m. to mainly 7 p.m. in June and July, because this picture has been developed by Northern Hemisphere. To finish this unit, we must study the size of solar field. The solar field size is very important because it represents over between 30 and 50% of the total investment, and it represents the catchment area of the solar thermal power plant. However, it must be taken into account that is set for parabolic disc because they are units. A solar thermal power plant always have a solar field overdimensioned because the incidence angle varies throughout the day. So we are able to determine the energy produced over a 10 minutes period thanks the solar thermal power plant generator, power rating, equipment features, and solar year type data, because we must understand that the electrical energy produced thanks the generator, this is the gross power, and we must delete the electrical energy consumed by the auxiliary systems, and we would obtain the net energy. So you have successfully finished the potential generation evaluation study.